Okay, let's see what this all is about. So exercise 5 about OneWire components, or how to hook the OneWire component to PSoC5. Basically, here we have the black box. We start from our data acquisition system, basic data acquisition system you already did on the, let's see, exercise 3. And then it had this analog sensor, but what you need to do actually is to add there that OneWire sensor. So you start from the template of exercise 3, data acquisition, name the project as, well, some good name like your name, PSoC5 OneWire, and you already have there that oversampling ADC measuring the temperature with LM35 analog temperature sensor, and downsampling that to 2 samples per second and sending that data to WART in JSON format. Okay, next you would connect a DS1822 or yes, 1822 sensor. Let's see, what does it look like? Simple 3-pin component in TO92 CAN, or well, these actually can be on different kind of pinouts on different kind of cans, but anyways, I have this DS1822 Plus. As I said earlier, it's okay as long as you have 18.2 there, then the rest of the digits don't matter much, since all of these seems to be both pin and code compatible. But anyways, if it's different, then of course you need to find the correct datasheet for that, what you are really using. All right, so connecting to digital OneWire sensor to BC port. Okay, the data port, it will be port 12.2, so that's both in and out data. And then you might actually find that example code from Cypress developer community, or actually you might take it from this Maxim integrated OneWire communication through software, which I showed you on the video tutorial of this theory part. Okay, here's the OneWire communication protocol. Okay, and then of course basically you need to take a look at the data sheet. This is a slow device. You have 2 samples per second oversampling ADC already there. Okay, you might actually sample this once a second. It really takes some time for this device to measure the temperature. Another point to take a look at it, as I said, this is OneWire, which means that you can power it up from the data bus. Otherwise it wouldn't be called OneWire or something else. But this actually is OneWire, genuine OneWire component with power pin. So my recommendation is to use the power pin if it's available and if the power is easily accessible. Okay. Anyhow, so sample device only once a second. Modify the code. Wait a minute. I don't think that we need that part, since there is already. No, we don't need that, since there is already software for that. software with commands on, meaning these online commands. You still have these connect the COM port using terminal emulation program. Once connected, C get single sample, S to stream continuous, E to get emulated samples. Well, emulation, I don't know if that is needed. Use X to cancel streaming for samples. Okay, that's fine for me. Let's take a look at this device a little bit better. Okay, 3 pins, data at the middle, ground is on left. When you take a look at, if you are looking at it like it is on your hand with the this type marking marked, and then the power pin is on the right corner. Okay, power supply range is quite wide, so basically battery operated devices works just fine. And plenty of different solutions. This has only ±2 degree accuracy components, but anyways, it's econo, meaning it's cheap. Okay. Other things. Each of these actually have 64-bit serial code. However, you can also omit that code, and if there's only one single device, then you can use so-called addressless mode on the operation. But it gives you 9 to 12-bit centigrade temperature measurements, meaning that you can program the accuracy. The accuracy, what you program there, also for low accuracy you need less time. Quite simple. Okay, some details. Block diagram. Okay, it looks like there is quite a lot of registers. There's a temperature sensor itself, alarm high trigger register, alarm low trigger register, configuration register, and then CRC generator. So to make sure that the data transfer is going well, there's also cyclic redundancy check, what you can use on your code to make sure that the data is valid. And well, yeah, then there are some devices. Okay, the bits, what to send and what to receive. Okay, there's a translation table. So basically, if you have so the data temperature register is 2-byte register where you have practically on, let's see, digital table 2 gives a digital output for 12-bit resolution conversion. So basically you're using the lowest bits. So if you use that as a 2-byte word, then it should be just fine. Although you need some masking. These are in state S, which is undefined. Except that, okay, bit, it's actually C, not it's A, oh sorry. Yeah, for negative temperatures, that's a sign byte, which sign bit which is on each of these values. Okay, so that's how it works. And there's also the alarm signaling. We are not interested about alarm now. Powering can be powered by an external supply or is operated in parasitic power mode. Good. So it's fully compatible. So that's supplying parasite power, meaning that you actually hold this line to voltage, power supply voltage for a certain time, and then basically when you start the data transmission, then you would just blink that one and turn that one off. But with the external supply in this exercise, you don't have to worry about that possible external transistor. Okay, then it has also the laser to ROM code, which is a unique address for this one, and it's basically 64-bit, which means 8 bytes. 8 bytes, yes, 64 bits. So starts with the cyclic redundant check from the most significant byte. Then there's 48-bit serial number and 8-bit family code. Okay, and that's the most important thing what you need to know. Well, the second important maybe. For reading this one, you actually will be reading the scratch pad, meaning you need to read all byte 0 to byte 8, which is a cyclic redundant check. So in order to read the temperature, you need to read all these 9 bytes. And okay, configuration register, which means that you actually need to also tell that device that we want 12 bits. Of course you want 12 bits, that's the highest accurate mode on this one. So you actually write to configuration register, you will write 7F. Yes, 7F, which is that is 0, the highest bit is 0, other ones are 1. And okay, CRC generation, you need to also regenerate the cyclic redundancy check to check if the data is valid or not. Alright, hardware configuration, transaction sequence. There's plenty of details on this data sheet. Please read these carefully. First, initialization, then step 2 is ROM command, so you send the command what you want to do, and then function command. So these are 3 different steps. Okay, initialization, meaning that initialization sequence must be done, and basically using that OneWire signaling. Reset pulse transmitted by the bus master, of course, and then if there is a slave, then the slave is giving the presence pulse. Okay. Then the ROM commands. Yep, there are some flowcharts how this actually works, and so on. So you need to read that data sheet. So if you, okay, there is the some function command set, in order to do the temperature conversion, basically you would write 44 hexadecimal to the command register. Then the memory commands are right there. Okay, and yeah, quite looks complicated. Function commands, yes, it looks complicated, but it's not that bad actually. There's initialization timing given, which actually is quite similar to what we had here. So reset is that age here 480 microseconds, and here it's yes 480 microseconds minimum. Then you let it the master lets this data signal line go high, and then master actually checks if there are any pulses coming in that next 480 microseconds. And basically the presence pulse can be any time. Let's see, or yes, actually it can be any time, but between 60 to 240 microseconds long. Okay. Then read and write time slots. Again, same as in here. Read time slot, detailed time read, okay. And there. So that's the device. But okay, this is nice. Operation example. This is something you can use as a reference when you are writing your own code to control that DS1822. It tells you what to do. So first, reset pulse to the line, then basically checking the presence, then master issues match ROM command, sends the ROM, and then transmit the ROM code, master issues convert command. This is when you know the ROM code. If you do not know the ROM code, then this does not work. Okay, this is the way I recommend you to do in this case. Reset pulse, presence, then transmit the command cc hexadecimal, which means for a single device that is on this bus, it says skip the ROM, you are the only one online. After that you can actually start issuing those scratchpad commands like 3 bytes to scratchpad, THTL, and configuration, and master issues. Reset pulse again, response with presence, and master issues skip ROM again, and read scratchpad, and reading 9 bytes, which basically will tell quite a lot of stuff from there. Okay, but anyways, you can figure out the rest. So on those 9 bytes, you would have also the data bytes. You just need to figure out which byte came first. Okay. So DS1822 operation example 2 gives you guideline how to write your the communication code with 1822, but in addition to that you need the OneWire engine, which follows this one, and there's a code example. What you need to do is do some you need to adjust this a bit. This tick delay here is based on 0.25 microsecond tick. We have the CY delay microseconds directly. So looks like you need to actually modify this code a little bit. So, but anyways, I believe that you can actually find the extra find this exercise quite straightforward after clearing all of this confusion. So practically your device, OneWire device, it has all the documentation what you need, is in especially what the temperature means, how it actually giving the temperature out, how it actually generates a cyclic redundancy check, okay, how the memory map looks like, okay, scratcher power map mode, how to read that, configuration register, and so on. So basically you can read the scratch pads, and yeah, you can do all sorts of thing with this one. Good. And then there's the timing diagrams, operation modes. If you know the 64-bit ROM code, excellent, good for you. If not, then actually you need to go and use this protocol, which you need to actually write the function. In this exercise you are not doing much on the PSoC. Let's go through some of that. So you start from this nice design of data acquisition system that works. You would then have one digital output pin, or actually digital bidirectional pin. OneWire pin. Data. Oops. And okay, bidirectional. Does it have a, wait a minute, why it has, interesting, it has also the terminal, internal terminal, so let me change that a bit, since we do not need the hardware connection, we just need the pin connection, and not drive, the drive mode is not strong, but open drain drives low. Okay, now that should work. You should be able to now read the pin and then set it to 0, and then you have that external pull-up resistor to hold the line to state 1. Okay, yeah. That's the way how you configure it. And basically now the rest of this design would be practically just adding some software. Try to encapsulate the software so that basically write all the software that you want to have in functions and preferably in main.c. I would like to see these functions without, or actually if I would like to see the functions so that I can give you some comments if needed. Yeah, so for that reason I'm asking only the main.c file on the return, so put all the code what you make in this main.c file. Okay, so that's the whole task. The return instructions are as previous. Nothing has changed. You just add OneWire sensor, get the temperature readings, and okay, transmit the temperature on UART again, and just add this one as a separate reading on JSON. All right, so let's see. Yes, there's also a link to the PSoC Creator System reference guide just for fun, since that actually tells you, for example, on the CY delay microseconds function, how to use it. Quite straightforward, but anyways, it's a nice document that also gives you what kind of the other functions they are in general. These are quite hard to find. This is on page 71, oh 70, on 70, page 73 from 101 pages that tells you about this CY delay microseconds. It took me for a while to find this document which tells you more about the this CY delay functions. Okay, so that's all what you need for exercise 5. The deadline for this one is May 11 at the end of the day. Okay, and the next chapter actually would be the project.